Okay, let me start. So this is a joint work. Okay, this is my joint work with Srinivasan from IBM, and it's about the invariance principle for positive spectrahedra and applications. Okay, first let me start from the basic. I think this is pseudo-random generator. This I think many of you already know. Is like this is standard definition in crypto and complexity textbook. And we say a function which maps, say basically it's mapped plus minus. Here we, in this talk, we consider the plus minus one instead of 0, 1, okay. And it's basically this, it maps less as plus minus one string to less than plus or minus one string, which is polynomial time computable. And we say it is a pseudo-random generator, or PRG, if for any probabilistic polynomial time algorithm, which if you feed in the input G, R, okay, feed in this R, basically you apply this G to the true random of length S, or you apply to the true random of length N, basically this algorithm, the difference is negligible. Negligible means, okay, one is smaller than any one polynomial. So basically, you can say that, okay, so essentially this says, okay, there is no polynomial time algorithm which can distinguish G, R, and true randomness. So we say these two are computationally very indistinguishable. Okay, then of course, this is very one like most basic primitive in cryptography, and also we know that this PRG exists implies one-way function exists, which further implies P is not equal to NP. So of course we, okay, so right, currently all this construction of PRG is assuming some computational complexity hardness. So now the question is, can we design a PRG against a class of PPP distinguishes unconditionally? Okay, so let's make it more formally. So let's see to be a class of polynomial time computable functions. And now we say a PRG G, which can epsilon fools this class C if for any algorithm or function in this class C, then the probability you distinguish the GR and the true randomness is at most epsilon. Okay. So please stop me if any of you have questions. So another question is how to fool this class C unconditionally. So is it possible to construct this G to fool?
So Penghui, just can you go back to the first slide? Just one minute. Polynomial time computable. Okay.
Yeah.
G itself is a polynomial time.
Yeah.
Yeah, and what? Yeah.
And you cannot do okay, then G, R, and true uniform cannot be distinguished by any BPP algorithm.
No, and what happens to what is the S like?
S is the seed length. I'm going to explain later. The S actually is the seed length.
Yes.
Yeah. So basically, you feed in the true. Basically, you just stretch the G is stretch this length S string to length N. And so you feed in the true randomness of size S and get to the distribution over length N string.
No, but when you say the PRG exists, implies P not equal to NP, right?
Yeah. Oh yeah.
I mean,
Okay,
there is a
yeah. So this is
because for S equal to N, it's trivial, right?
Yeah. Sorry, I should say that here. Yeah, PRG means exists if S is log N. Okay, S is
again
the log N.
And that will basically also de-randomize BPP, right?
Yes. Okay. Yeah. Yes.
So then PPP equal to P, but you're saying that in fact P equal to, not equal. That will imply BPP equal to P, right?
Yeah. But if the PRG exists, that means that you can imply that there exists one-way function, right? And one-way function exists will imply P not equal to P. Okay, but this I would say that informally. I mean, we need to adjust these parameters.
Huh. So for now you're assuming S is log n, right?
Yeah. Okay, yeah. Later I will specify what the seed length when we talk about a specific class of functions we want to fill.
Okay.
Okay. And okay. So anyway, so now the question is, if we are given a specific class of BPP algorithms, so can we construct a PRG that fools this class C with this seed length as small as possible? Ideally, we want this S to be like polylog in N and hopefully also polylog to 1 epsilon of, okay. So there are there are a lot of work, maybe like I would say almost like several, almost like several dozen papers. And okay, because first I will claim that I'm also new to this area, so this definitely is not a comprehensive list of the related work. And okay, first model or computation model people are interested is like based on circuit, such as like a read once branching programs or the read once CMF and also read once AC0 formulas or AC zeros and unbounded depth read once formulas. So there are a lot of works about to designing the efficient PRG to fool all these classes. Okay, then there's another line of work which try to fool here I call it geometric sets. So first is a half space, which is basically this. In this case, the distinguish is pretty simple. Basically, you just find a bunch of real numbers A1 to AN. So if you get the string, you sample X and just check whether this summation xi AI is less than B. If it is less than B, I just say, okay, it is true random. If it's greater than B, I say it is withdraw from the student, this PRG. And the question is, can you design a PRG that fools all half spaces? And this still also have a lot of works. It starts from 2010 and until very recently, this is a state of art cylinder. It's like log n over epsilon, log n over epsilon square.
Sorry, Penghui, so in the bracket, you're describing a class of D?
Yeah. This is basically any half space, any such distinguishers cannot distinguish the PRG the PRG you construct.
Okay. So the distinguisher takes as input x1 to xn and then just checks this.
Yes.
Cool.
Okay, and then after that, basically now there are two. I think there are two different branch generalizing this work. First, we just view it as half space view it as a polynomial. So half space you can view it as a degree 1 polynomial, so you can consider a higher degree. So which is like a high degree polynomial threshold function. So it still is quite simple. You just choose a say degree D polynomial, and when you sample X, you just fit in this polynomial. You check whether it's less than B or equal to B or greater than B. If less than B, you say it's true random. If it's greater than B, you say it is still random. And this is there's okay here also there's many works, and I think this year the stock this Adorno, Servideo, and Liang Kang he gave the state of our result is the C length is D over epsilon O to the log D dot log n. And there's another line of work, basically another branch we consider it as a half space as a geometric project. So instead of consider a half space, we consider intersection of half spaces, which here is called the polytopes. Again, there are also many works, and I think the same set of authors. They give a best seed length is poly log m. M is a number of number of half spaces, and one website log n is the length of the string. Okay, so as since I'm from doing corner, since I'm trained by Rahul, so when I see polytopes, the first thing I view that as a linear program, and immediately I say, okay, let's do it for semi-definite program. So okay, so we consider the can we fool something called spectrahedron? Spectrahedron basically is just a feasible set of semi-definite programs. Okay, so semi-s we such that summation I xi ai. Oh, sorry, there's no j. Sorry, there's no j now. Just summation ai xi ai is less than b. Here less than b is a lower order. Okay, here ai b are all matrices, Hermitian matrices. Here we only work on the real space. So all these AI B are symmetric matrices. Okay, so why we are interested in this spectrahedron? First, okay, it is a generalization of polytopes. That's very easy to see. If all these AI B are diagonal, then basically it boils down to polytopes. And second, if we know that because this summation AI xi ai less than b basically means b minus summation xi ai is positive semi-definite. Now you're using the Sylvester's criterion. It can be written as an intersection of polynomial threshold function. Based on all this, I'm going to elaborate this a bit later. And third thing is this spectrahedron have a rich power of expression. It not only contains polytope, it also has like cylinders, electopes, or etc. Blah, blah. And this is also an important object in both polynomial optimization and algebraic geometry. And last is that our understanding of spectrahedron is still pretty poor. Even proving some geometric object is a spectrahedron is pretty hard. Okay, and then now this is our main result. We show that you consider a class of spectrahedron, the summation xi. Sorry, I'll just ignore this for all j. Okay, summation xi ai less than b, where if all ai are positive semi-definite, and this is positivity, and we have imposed a regularity condition that summation ai square is lower bounded by identity and upper bounded by some constant times identity. And each ai is less than tau identity, which in all ai are small. Then we construct a PRG fools this spectrahedron with C length log n times poly log k and polynomial and m 1 over delta and the normal b, spectral normal b. Okay, and so yeah. So any question about this main theorem?
So where does tau enter in the theorem?
Okay, tau actually just view tau like delta. Okay, tau is something like delta.
Okay.
Where is the small m dependence? Like
M?
small m. They were like
small. Oh, sorry. Sorry. No, there's no m. Sorry, this is for all gems. There's no m. Sorry about that.
okay.
Yeah, just ignore this for all gems. This part. Yeah, and this k is k beyond all this k is the size of the matrices.
right.
Okay. And okay, here two things. Okay, first the big positivity is something. Yeah, because of some technical reason we need to do that. And the for the regularity, this basically is also the assumed at the early work about when they doing the Fooling polytopes and the Fooling half space. Okay. And of course, later they developed some new techniques to remove this regularity condition, which I'm going to also explain later. Okay, now this is the outline of my work. First, first I'm going to explain something called Invariance Principle, which is the key to designing this PRG. And classic, and we prove that actually first this class, and we are going to explain what is the Invariant Principle for spectrahedron, and then we prove at the concentration construct PRG, and finally I make a summary and at least some open problems. Okay, first I'm going to explain what is the invariance principle. Before going to the details, first I'll recall what is a central limit theorem. And this this is a, I think I would say this is a simplest version of central limit theorem. So if we have an IID distribution, which is each xi is half minus one, probably half minus one, probably half is one. And you consider distribution S1 sum xi divided by square root n. And we know that this will be would converge to a Gaussian distribution, standard normal distribution. So basically it's like, right? And okay, now let me rewrite this. I rewrite this CRT in this form. This way, let's define the function psi, which is 1 if x is less than a, 0 otherwise, and I view this inside function s1 plus sn divided by square root by as a polynomial. Okay. Now, you can write it in this way. You compose psi with this polynomial p, and this take a limit, and this expectation basically is a probability, right? Summation si, this probability, and here is a. This is here because note that if you sum n independent normal distribution and divide by square root, you get back to a normal distribution. Okay. And this is a qualitative version. And if you want to see the quantitative version of CRT, that this is called Bayesian. So basically, how this quantified how fast the limit converges, and the difference is upper bounded by a constant divided by square root n. So again, I can rewrite it in this way. There's composition of a function with a polynomial. Now you can, if you go to you can also check it. This is also true if this x1, x2, xn are all 1 over epsilon square y is uniform. Okay, this means it's any distribution if you take out any 1 over epsilon pieces, it looks like a uniform. And so this means you don't need, then this means you can actually find a design a O1 over epsilon y uniform distribution, which gonna do looks like a Gaussian distribution. And using this, you can construct some PRG fooling this function s1 plus xn divided by square root. Okay, this I'm going to get into more details later. Sorry?
Is epsilon 1 over n?
Okay, no, yeah. If you just want this less than epsilon, then it is O1 epsilon. But here epsilon should be 1 over square root n. Okay. Anyway, I'm going to this later. And so around then later this result was generalized to a higher degree of polynomial. So of course you may ask what to what extent this inequality still holds. If you just want this less than some small number, can we get can we work? Does this still work for other functions psi and other polynomials p? Okay, and this is called the Invariance Principle, which was proved in 2010. It shows that for any polynomial, if the variance, okay, if the input x is uniform distribution, the variance is upper bounded by constant, and this polynomial is low degree, and each coordinate, the influence up is small. Here and the influence is defined to be if you just randomly choose x and you flip ith coordinates and see what's and then you check the difference square, take expectation. Okay. If the influence is this basically measures how much does the ith coordinate influence the global input, the value of the function in expectation. And this is okay. This is a restriction to the inner function, and for the outer function psi, it must be okay. It should be very smooth. It should be a 3 times differentiable. Basically, you have a 3 times derivatives, and the third order derivative is upper bounded by constant. Okay, this third order derivative basically just summing all possible 3 times partial derivatives. Then this expectation composed, the psi composed with p. These two values are going to be upper bounded in this way. Okay. Okay, and then I'm going to give a sketch of this invariance principle because all the remaining work for designing either the half space, polytopes, and spectrahedron are built on this framework. The proof of this invariance principle basically uses the very standard hybrid argument. Because we want to argue that these two distributions are same if you replace all x by g. S are here now S is like uniform distribution and G is standard normal distribution. So we just do it by hybrid argument, just replace one by one. So then now you just now you compare the two when you substituting when you replace the I+1 coordinate. Okay. Now you can see this actually if you because this is P is a polynomial, so if you expand it, then you can actually have two paths. The path which contains the I+1 variable. The path which does not contain I+1, right? So if it does not contain the I+1 variable, then these two paths should be same. Because here the only difference is I+1. So only the difference is the term which contains Si+1 and the term contains Gi+1. And now, okay, so now I just explained that the term which does not contain Si+1 or Gi+1 are same. And the term which contains Si+1 or Gi+1, you can check this actually the expectation of the square. It is influence of ith coordinate, which we assume it to be small. So you can see now, if we want to argue this difference is small, you can see basically both sides are actually acting on a term which is same, but perturbed by something small, right? So a natural choice, we just apply the Taylor expansion. Taylor expanding this function on this common terms. Okay, so what they do is, okay, you do a Taylor expanding, you do the first, okay, this just standard, and you just expanding to the third order. Okay, so here should be 3 prime. Okay. And then you argue that, okay, because the first term is same, the second and third term also same, because you can check, because this second and the third, the first order derivative and second order derivative, they only either contains one SI or two XI, or one SI or GR, one. So the first order is like, here you can contains one XI, here's going to one GI, here's two XI, here two GI. And because these two distributions, the first moment and second moment match. So these first three terms match. So the only difference is the third order derivatives. And the third order derivative can be upper bounded in terms of influence of P. This, okay, here it requires some non-trivial, but it's not relevant to this talk. So I'm not going to explain in detail. But here I just mentioned, here you need something called hypercontractive inequality. Okay, so this is basically the high level of the proof of this classical invariance principle. So any question? Okay, good. Okay, so now let's see how to apply this thing to get back to a Berry thing. Remember that we need to say this size should be, okay, it is prove this main result, we need to assume this size not only smooth, it should be like 3 times differentiable. But the invariance in this side actually is even not continuous. It is a step function. How to resolve this issue? Basically, we need to introduce something called a modifier, which actually is a smooth approximation of psi, which is psi theta. And this psi theta is okay. It must be differentiable, and the derivatives should be bounded. And the choice, the standard choice is just do this. Okay, choose this function. Okay, this, okay, I'm not going to explain how to do it. I'm going to say how to get this. When you get this, and okay, this function will look like this. Okay, this blue line is psi, and this yellow line is psi theta. And you can see if it's far from this A, both are pretty close. But in this area, it'll be, the difference will be big. But then how to avoid this? Then you need to prove something called anti-concentration. Basically says the probability mass concentrated on this region is small. Okay, so basically with high probability, you are either here or here. Then you can argue this two, then you can get the very thing. Okay. So now let's go to the fully spectrahedron. Basically, we are doing the same thing. First, we define the function psi, which is 1 if S is in the spectrahedron, is 0 otherwise. And we design a modifier, which is if infinitely differentiable and also the derivatives are bounded. And okay, and okay, then we can argue that okay, either this if it is far from this boundary or is pretty inside this region, the psi theta and the psi are close. But when you are close to this boundary, we gonna need something called, we need to prove anti-concentration. Okay, if we have these things, then we are done. Okay, so that is basically that is a high level of the proof. Okay, now let's see how to, okay, so the proof, so the whole proof, the proof sketch first, okay, we design a modifier psi theta, and first we prove the invariance principle for this psi theta. So basically we replace uniform distribution by standard normal distribution, these two are close, and then second step, we argue that this invariance principle also holds for all log k wise uniform. Then third, we prove anti-concentration. But after we have all these three pieces, then we can say, okay, psi u is close to psi theta u because of anti-concentration, and psi theta u and psi theta g are close because of invariance principle. And these are close again by invariance principle, but we know it holds for all log k. And psi theta is close to psi again by anti-concentration. Okay, and that's it. So is it clear? Okay. Now let's go to see what is a modifier we're going to choose. Basically, we choose a modifier called Banker's modifier, which was introduced by Bankers in 1990s. And because he considers such a function, we input is S1, Sk, and it is indicator that maximum Ixi is less than 0, at most 0. And you define the Banker's modifier basically like this. You just take expectation G is a K independent standard normal distribution, and B acting on S plus theta G. Theta is parameter you can adjust. And okay, and there's some standard the two properties. First is Banker's proof that first B theta and B are close if you choose theta pretty small. And second, the B theta, the T times derivative is upper bounded by log T over 2K. So we are bounded. So you have bounded derivatives and closeness. So this perfectly fit to what we need. Okay, and also the previous all these half space, polytopes, all these things they choose all of this they choose the same modifier. They all choose this Banker's modifier. Okay, but now that we want to apply this Banker's modifier to matrices. Because let's say because now we want to full such a set summation xi ai minus b at the most 0, right? So we want to add this modifier, Banker's modifier, to the eigenvalues of this eigenvalue of this summation xi minus b, right? We want all the eigenvalues. The largest eigenvalues is at the most 0. So we want to prove the invariance principle for this matrices, especially we want to get something like this. If you replace this X uniform by the IID standard normal distribution, these two expectations should be close. Okay. Okay, and again we use hybrid argument. So we do a replacement 1 by 1, and then now you can see with this inside this summation xi, you split two parts. Okay, when you replace the ith coordinate, and so they have a common part which is from 1 to I minus 1 and I plus 1 to n and b. This is a common part. And there's a different part. Here is xiai, another guy is giai. And you check that this is a norm, the spectral norm, this xiai, because xi is either 1 or minus 1. And giai here norm, basically you take expectation. So both norm are AI. And then because by the regularity assumption, we assume this AI, we remember the regularity assumption AI is less than tau identity. So basically now you can see this G theta are acting on P but perturbed by some small matrices. So again, we again use the Taylor expansion on G theta at P with respect to XIAI and GIAI. Okay, but now note that now we are actually do a Taylor expansion on functions acting on matrices. So we need to make use of something called the Flesch derivatives, which is defined like this. If your function f a, you will take the derivative on a with respect to direction b. Then you just do this. You take limit f a plus sb minus fa divided by s. You take s to 0, and you can do this. Take the derivative again and again to get a high order derivatives. This actually is a derivative. This is a derivative. Even they can define it even in the Banach spaces, and it also shares many properties with derivatives in Euclidean space, like composition rule, linearity, addition, multiplication, blah blah blah. This is a good thing, but the bad thing is it is usually very hard to compute because of all the matrices are non-commutative. Here I give two examples. First, suppose you will compute the derivative of s to the n, okay, a to the n, then take derivative of p. And when you take derivative, you will get n minus 1 of n terms because this a, I, b are non-commutative. But second, if you this is still okay. But what happens if you want to compute the square root a? Derivative square root a with respect to b. You compare this will be the solution of this function square root a s plus s square root a plus b equal to b. That it is a solution, and you can check actually if a is positive definite, this function, this equation has a unique solution, and that is the derivative. Okay. So you can see even if you get square root, the computed derivative will be much more complicated. Okay. But again, there's still but good thing is there are many mathematicians. No, I will say many there's some mathematicians work on these computing Flesch derivatives for many years. So we are lucky we get to know. That's a result by Sandoff, who gave who actually he proved that first if f is symmetric and is t time differentiable, then when you compose the f with lambda eigenvalue, it is still t times Flesch differentiable. Okay, first I forget. We need to introduce called spectral function. Okay, basically f is symmetric. It's a k variable function map RK to R. It is symmetric means if the value is same, you just permute the impulse. And you can define f acting on symmetric matrices, which basically acting on all the eigenvalues. Because it is symmetric, so the order of these eigenvalues does not matter. And the Sandoff proved that if f is t times differentiable, then this capital F is also t times Flesch differentiable. And moreover, he gave a way to compute any order of Flesch derivative of f at a with respect to ab. And the it gave a way to compute, but you need to compute it recursively. I'm not going to give how the computer is a bit involved. But I would say, yeah, here so I just list what is a third order of derivative. If you compute third order Flesch derivative, it is with the summation of these 7 terms. Okay. Here the xi, basically here we assume this input at p is diagonal matrices. Okay, now, actually, no, but of course we are not interested to compute the third order fraction derivative for arbitrary function. We only interested in the Banker's function. So we compute the fraction. We first compose the Banker's function with the spectral functions. We get this. We compose Banker's modifier with this lambda. Lambda is the eigenvalues of the inputs. We get g theta, which is special function, and we're going to compute the third order derivative, third order fraction derivatives of g theta acting on p with respect to h. Okay. And you can, we managed to compute it. It's going to be upper bounded by this. Okay, this data is, we assume data is the largest eigenvalue of p. Basically, we assume all these xi are upper bounded. And the log cube k is the dimension of the matrices, and h is spectral norm of h to the cube. Okay, and I'm not going to go into any detail of this proof at all. But actually, our paper, almost half part of our paper are devoted to proving this. But it's okay. I would say it needs some very long, involved analysis, and I don't figure out how to present that in a clear way. But here just list some techniques we use. First, we make use of the standard result, and we are bounding the terms we listed in my previous slides, like one by one. And we expose some new properties of Banker's modifier, and we also use some make use of divided difference representation of fraction derivatives, which was proved by mathematicians many years ago. And we also prove use this mean value theorem for divided difference. And the last thing is we know there's a nice expression of fraction derivative of the exponential function, which is called Dyson expansion. Okay. Okay, then that is all I want to say about this thing. Okay. Okay, now this is the first part. Now we've already proved that using this, now we can already get at least prove the invariance principle for modifier. But then the next piece we need an anti-concentration. So anti-concentration basis that the probability mass concentrated on this boundary is small. So in this context, basically we will say the probability is, because now the boundary, so the summation xi ai minus v, largest eigenvalue is close to 0. Which with this probability we want to argue this will be small. And here we need to make use of assumption that this tau is pretty small. Okay. Okay, and now let's consider this set. Okay, this x, all this x such that this lambda max, this larger eigenvalue summation xi minus b is close to this boundary. Let's consider a scenario if all this AI, the minimum eigenvalue is large. Okay, here of course it's not true because we already assuming this AI is small. Okay, but anyway, let's first assume this AI minimum eigenvalue is pretty large. Now you can see if for any x is in H, if you flip one coordinate, well, if you flip one coordinate, then either you initialize minus AI change to plus AI or plus AI change to minus AI, right? Then the largest eigenvalue will change by at least tau times log k. So that means if s is in H, you flip one coordinate, you will get outside H. So that means for any s is in H, all its neighbors will be not in H. If a set satisfies this property, then HOSD, they prove that this size of H cannot be big. It will be upper bounded by 2 to the n by square root n. And later you can even further improve that if you can show that at least alpha constant fraction of AI, the minimum eigenvalue is large, which actually implies for any x is in H, at least the constant fraction of its neighbors are not in H. Then this H, then this size of H is not big. Now this is quite intuitive. Right? If the size S is big, then for any so there should be many elements there. The neighbor should be also in H. Right? So, now, but is in our scenario we don't have such condition. here we all AI is very, very small. So what we do is basically we do a random partition. Consider a scenario. Initially, we have summation x AI. Basically, each AI you are assigning either a random, either plus, minus, right? We first do a random partition. And we partition this A1 to AN, okay, to M buckets. And in each bucket, we are even further to sub-partition to 2. And now I consider, okay, if all the AIs which are in this blue area, I just assign to plus. In this yellow area, I just put assign to be minus. Okay. And okay, plus minus plus, and it's not hard to argue that this distribution, the way we sum this distribution, this will be same as when we're doing summation XII. But since we are doing grouping, then you are making use of the metric channel bound. You can show that with very high, if this M is pretty big, or large constant, then you can show with almost close to 1 probability that at least 3/4 of this AI star, is AI plus or AI minus, the minimum eigenvalue is large. Okay, so once after we get this, then we can plug in the OSD result says, okay, now the size of this boundary is not big, then we get any concentration. Okay. And now since now we have two pieces, we have the invariance principle and we have any concentration, then we can make use of, we can design a PRG, and here we just use a very standard PRG, which is designed by Michael Zuckerman several years ago. Okay, and basically first you choose a 2 log k-wise uniform H, and okay, and then you design also choose a bunch of this also for S to M divided by T. Okay, I'm not going to the details of this, but I just say this is a standard way to construct a pseudo-random generator, which is all log k-wise uniform. Okay, we see that pretty small. Okay, and make use of this, and then just fill this. You can prove that this PRG will fool the positive spectrahedron. Okay. So that make a summary that first we prove the invariance principle for Banker's modifier as a spectral functions. And okay, the second part actually I did not talk here. We also prove some geometric properties of positive spectrahedron, such as like sensitivity, noise sensitivity, Gaussian surface area, blah blah, all these things. And last thing we prove we give an efficient PRG for regular positive spectrahedron. Basically, we prove the Michael Zuckerman's PRG still fools the positive spectrahedron if you adjust the parameters properly. Okay, then here I list some further open problems. First, okay, you can see here we assume the spectrahedron is positive and regular. So of course, a next step is, can we remove this regularity and positivity assumptions? Here I can make some remarks first. For the regular, okay, when we consider the Fulling half space or Fulling polytope, the regularity was removed, but they reduced some combinatorial object like a CMM or things, but we don't know how to make those techniques work for spectrahedron. And the second part is positivity, and I would say this is a unique spectrahedron. You won't meet, because when you consider polytopes or half space, because it's basically just a bunch of half space. But if you want to remove the positivity, yeah, you need to analyze the changes of this eigenvalue. This will be, I think here we will need some new techniques that will be different from our classical work. And second thing is I say just I always say that summation xi less or equal to b. If you use the Sylvester criterion, basically it is all the determinant of a principal minus of summation xi minus b is at the most also we determinant B minus summation xi. The principal minus the determinant is at least 0. So this can be viewed as to full the intersection of polynomial threshold. So for the case, so can we use this framework to get a larger class of polynomial threshold function about this invariance principle or PRG? And the last is, do we have the invariance principle for general spectrahedron? So general spectral functions. And to get this here, okay, here's concrete math problems we are facing now. Here's consider if you have a symmetric function f, which is a k variable function. The symmetric, now we consider that it's analogous spectral functions. And further, we assume that it is all the teeth time derivatives are bounded. Okay. Now we can define the teeth time threshold derivatives. Now you can see if A, B are all diagonal matrices, then you compute the teeth time threshold derivative of capital F. It's not this is not how you will upper bounded by C times trace B to the T. B is just take all the entries, but B is not diagonal. So you just replace diagonal entry by absolute value. And this is, you can further rewritten as the C times trace square root B dagger B to a T, which actually this is a Shannon T norm. Okay. Now the immediate question is, does this still hold for Hermitian matrices? So is it even still true? Is it even true for T3? We only consider third order derivative. And right now we just prove the class. This all basically we just prove this holds for Banker's modifier. And in my previous work about this noisy EPR games, noisy quantum games, I prove another class of game, another class of functions. So right now we only know 2 classes of functions, which this holds. So the question is this true for arbitrary function for F? If this is true, then I think, yeah, it will simplify a lot of things. Okay, that's all my talk. Thank you.
Are there any questions to Penghui?
Oh yeah, I have a question. So could you give some intuition in the classical case about the how do you call it, vectors modifier?
Yeah. So,
You defined it earlier, but I didn't get much intuition.
yeah.
Right. Yeah. So how does it work exactly classically?
Oh, I think you get back to here will be easy to see. This one will be, you just consider if case 1, and basically you are gonna to get this is for case 1. This is Banker's modifier for case 1. And you also I think maybe let me get. You guys see, okay, your question is why this is close to B?
Yes. Yeah.
You just think about if theta is very small, then basically you if theta is very small, then you want to if you okay, this theta then you want theta g change x, then you need really make this g to be really big, and the probability that g is big is small. That's it. Okay. And this is smooth because and this is infinitely differentiable basis because of this actually it is a convolution of the function b, and the probability density function of the e to minus s square.
Oh, I see. Okay. All right.
Yeah.
Thanks.
Okay, thanks Penghui for the nice and yeah, looks like a pretty involved work. So I'm trying to understand just the very basic case. Okay, your starting point is this concentration bound. Okay.
Yeah.
All right.
Yes. Yeah.
So I'm saying that looks like that you know the function that is being fooled is the sum function, right? Or in
Yeah,
fact,
yes.
like I mean, kind of some kind of a threshold, like some
It's only,
average being less than a.
Yeah. Yes.
So here, see, initially you have like x1 to xn IID, okay, okay,
Yeah.
and then G is basically, I mean, kind of the expectation of each one of them, and
Yeah.
then you are also summing, you are also taking these several G's, which are also just again independent G's, right? I guess each one of them.
Yeah.
Hmm?
Yeah.
Okay, where is the saving here? The saving of the randomness happening. I mean,
Yeah. Basically, you first prove this, and then okay, basically you first prove this by, and then basically then you're gonna to check how many randomness is still okay to make this work. And then you can check, okay, yeah, that's basically all this invariance principle proof. Later you can check. You don't need to require this xi to be very random.
yeah. So what is so that is I think you're saying in the next slide, right?
Yeah. And the reason, roughly say why this works, because okay, this here the proof.
Yeah, there's a 1 over epsilon square
Yeah.
that thing.
The saving happens because when this works, because you can see basically you only need to go to the third order term. So basically you only care about the third moment. So basically you need two distribution with the third moment that matches. That's enough. That's it. Okay, this is not very rigorous, but it's you only need get distribution which up to a certain moment match to the Gaussian distribution. That's enough. So you don't need like a true random. Oh, yeah, no. So up to certain moment, you match the true random. That's enough. You don't need to like a true random match to you with k. Because the say k-wise uniform, the whole point k-wise moment because up to kth moment, it matches the true randomness, and that's enough.
Yeah. So for the sum function, right?
Yeah.
So
Okay.
I mean, just for the sum function.
Yeah.
Sum function, you're saying 1 over epsilon square y is uniform distribution implies PRG of seed length. Okay. So here.
Yeah.
Here. Okay. Here. Okay. So here you will take what you will take x1 to xn not being all IID, but only like what 3 y
square y uniform. Yeah.
Huh?
Yeah. It is. Yeah. S1 to Sn, which are 1 over epsilon square y uniform.
Just 1 over epsilon square y is uniform.
Yeah.
Okay, and then you will say that also does the same thing. Huh?
Yeah, that's the same. Yeah.
Okay. And the thing that you describe later are like the proof of this fact that 1 over epsilon square y is independent is enough.
Yeah. Basically, the whole proof is first proof for true uniform. Then you just verify every step. Okay, how many y's uniform is, how much y's uniform is enough? I check step by step. Okay, that's enough. That's it.
So, and why does it stop at this what third derivative or what?
Because the third order derivative.
So basically, see, this is basically, I mean, this is the Chernoff concentration, right? I mean, instead of Gaussian, why do you have to take just Gaussian? You could take any any distribution, no? Or what will happen here?
No, that's because CRT or central limit, you anyway all this you go to Gaussian, right?
No, I agree, but I'm just saying that your xi's, each xi, right?
Yeah.
I'm saying could have its own distribution. I mean, it doesn't have to be like half plus minus one or something.
Yeah. Of course.
I mean, we know the concentration happens, the Chernoff bound, right?
Yeah. Yes.
So, and in fact, you don't even have to take this threshold A, right? You know that the whole sum actually I mean, the average looks like the expectation.
Yeah,
It
yeah,
doesn't
yes,
even
yes.
have to be like a threshold, right?
Yeah,
I mean, you can, well, that's already a smooth function. So, you know, all this work that you're doing to first make it a threshold and then smoothify it and this and that,
yeah, 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 yeah.
right? I'm saying that, no, just go back to that slide only, this one only, you see? If you look at this function, x1 to xn and averaged out, whatever, right?
Mm-hmm.
That function is unable to distinguish between, you know, then you'll have to argue that it is unable to distinguish between the expectation versus this thing, right?
Mm-hmm.
No, like true IID versus a limited independence.
Yeah.
Okay.
Mm-hmm.
So so I'm just saying, so here you're doing it for a particular this threshold. I mean, I'm just saying that, can you just, do you have some implications already for the Chernoff bound itself, that in the Chernoff bound itself you're having a fast concentration without IID? Yeah.
Yeah, that is. I think I discussed this with Anurag. Okay, discussed with Anurag sometime. The difference of here, the CRT and Chernoff, the proof is quite different, because the Chernoff actually really, because you go to Chernoff bar, you need to go to this characteristic function. Then you need to the e to minus x, which you request infinitely many moments, not only for you, but right? E to minus x. So it contain, you have some requirement for all moments. But for CRT, you only need to third order moment. And yeah, I tried to prove using this framework to first reproduce a channel bound. But similar channel, you really need much higher moments to make it work. Yeah.
Okay.
Any more questions? So if not, maybe we should thank Penghui for kindly agreeing to give talk, and maybe we can end the call.
Okay. Thank you. Yeah.
Okay. Thanks, Penghui. Thanks.
Okay. Thank you, Rahul. Thank you, Naresh. Yeah. So.
Thank you, Penghui. Bye.
Yep. Bye.